Ron and Paul.
Thank you. Thank you very much. Good morning, everybody. Pleased to be with you this morning. And as you just heard, I am an old-timer with my first ham license in 1963. 10 years later, I found myself, we can do the slides now, okay? 10 years later, I found myself at my first TV job, and that was actually a picture in Nashville, but my first TV job, I entered the high-paying, very high-profile broadcasting business in a television station in the middle of a cow pasture. It was in Terre Haute, Indiana, which was my hometown, and they co-located the transmitter and the studio to save money, and the town that it was licensed to was actually Terre Haute, Indiana. You ever hear of that? Went back there to see the eclipse a while back. It was pretty neat. But the transmitter was 16 miles south, and it was in the middle of nowhere. And I used the high-tech technology of the day. This station had only been on the air at that time about 20 years. This was still kind of the beginning of television in these small markets. I had a plexiglass-covered national map on which I could draw fronts and high and low pressure centers. And I had a map of Illinois and Indiana with similar plastic on it, and that was about it. But we had just gotten a new avionics radar, an RCA AVQ-10, which was a C-band 5 gigahertz radar, put out about 300 watts peak, I think. Had a flat plate array antenna, which was made to be mounted upside down in an aircraft. Well, we modified that and put it right side up. We had a 400 cycle dynamotor power supply to run this thing. This is where the ham radio comes in, right? And we superimposed the image from that radar over a studio camera shot of a nicer looking map and tried to get it lined up as nearly as possible. And that was pretty cool because no other television station in the area had any radar pictures at all. Well, about 9 months after I started, we had a historic event. Terre Haute was not exactly in the track, but there were many nearby, and I was seeing radar pictures, the top of these thunderstorms, at a distance that I had never seen thunderstorms before, like down over Cincinnati, 160 miles away. And as it turns out, this was a historic outbreak. You still remember this in Tennessee from the Cumberland Plateau tornadoes. Down in Huntsville, Alabama, they were hit twice during that day. There were 148 tornadoes in 13 states. At one time, there were 15 tornadoes on the ground at a single time, at a point in time, and there were a record 355 deaths in this outbreak. One of the worst storms was this one, which is in Xenia, Ohio, and it resulted in quite a number of fatalities. At Xenia High School, they were practicing a play on stage, and they got the alert that a tornado was coming, so they got everybody into an interior hall, which was their tornado drill area. And about 5 minutes later, the tornado picked up a school bus and deposited it on the stage. So, you know, that was the kind of thing that was going on April 3rd, 1974. This actually was not our AVQ-10, but this was the weather surveillance radar from the National Weather Service in Cincinnati. This is what the technology looked like at that time. This was the WSR-57. And what you saw was a black and white picture, and maybe if you were lucky, you could see that Xenia, Ohio hook echo. So one of the things that I determined at that time, and so did everybody else in the weather community, and that was, you know, we need a better radar. Fast forward about, 37 years, and this is a picture of the next rad in Nashville, the SR88D. And this was in another very eventful day in my weather career. This was April 16th, 1998, with a number of large supercells crossing Middle Tennessee. One of those came pretty up close and personal. This is the view from our Skycam. And Joe Case, who's now passed on, and I were watching this thing come in. We had been watching this supercell come just to the south and east of us, and there hadn't been any reports of anything but large hail. But we're seeing the transformers go, the power lines shorting out, and a tornado heading right for, not where the camera is exactly, but a little bit north of where the camera, and we realized, I think we both realized at the same time, we look at each other, that's where we are. So this was the video that led the CBS Evening News that night, as this large tornado is moving through Nashville on our Skycam. As it turns out, we lost power not too long after that, and with it, this was before Channel 5 had an emergency generator, which they now have after this. We lost our ability to communicate with the outside world, and it was a scary day, to say the least. But the warnings were good. And the radar technology had improved so much that television stations were able to track this thing. Not so much us, because we got knocked off the air, but the technology had improved a lot. I think this was a really important day for tornado and severe weather awareness in Middle Tennessee, just as Huntsville has always been a very sensitive television market to tornadoes, more so than Nashville, until this happened. Kind of the idea that, well, you know, tornadoes do happen in Middle Tennessee, but they tend to happen out in the middle of nowhere, and we're not too concerned about them. But that changed it. When a tornado hit downtown and everybody knew exactly where it tracked, awareness, you know, groups like amateur radio, the amateur radio community got more energized in terms of being spotters and trying to help us with this problem. Another thing that happened on that day, let's go ahead to the next one. This is the only documented F5 tornado, EF5 actually, to ever touch down in Tennessee. This had a 19.3 mile path, mainly in Lawrence and Wayne County. And there were substantial homes that actually had anchor bolts that were wiped off the foundation. There was a pretty good stretch of pasture land where the grass had been ripped up from the force of the winds. So this is a pretty dramatic tornado. That was one of the tornadoes in that April 16th, 1998 outbreak. So we really had to go until 2011, the Tuscaloosa tornado, that big outbreak, to find a worse tornado outbreak than this one. But 1974, I'm talking about now, this one was not that bad overall, but in Tennessee, this was a big outbreak. The next big outbreak was 2011, and that was the Tuscaloosa tornado. All right, so today, what are we going to try to do? Well, Paul, and I just want to thank Paul for all of his service, not only to the amateur radio community, but also to our community in general in trying to promote awareness for storm spotting, to get groups energized and trying to help us solve this problem. We're going to talk about tornadoes in Middle Tennessee, when and how they form. We're going to talk about the kind of thunderstorms that produce tornadoes, and we're going to talk about observing and, above all, safety in tornadoes. When do tornadoes occur? Well, this is a graph from the National Weather Service data that shows the monthly totals of tornadoes. Do we have a laser on this?
There is a laser, but it doesn't show against that screen.
Okay. There you go. The peak in the month of April is 212. That's easy to pick out. May, where we are now, a pretty dangerous month, as we just saw on Wednesday. The least likely time to experience a tornado in Tennessee is in the late summer months and the early fall. One of the reasons why that is because the temperature of the air pretty much matches the temperature of the land most of the time. There are no big swings in temperature usually. High pressure dominates the weather. You would be least likely to experience a tornado in July, August, and particularly September. But note there's another definite peak that comes about in November and December. And we were reminded of that, December 9th of 2023 when the tornado hit Hendersonville, and there was another one up in the Clarksville and southern Kentucky area. In 1999, a vivid example of wintertime tornadoes in January, I believe it was January 17th, 1999, an EF4 tornado hit Jackson, Tennessee. 5 days later, at 4:15 in the morning, Clarksville was decimated, downtown Clarksville, by an EF4 tornado at 4:15 in the morning on January 22nd, 1999. Those of you who've been around Franklin a while probably can remember in 1998, on Christmas Eve morning, a tornado moved through where it now is McHatcher Parkway, it wasn't there then, and one fatality occurred not too far from here when a tornado occurred at 6 o'clock in the morning on Christmas Eve morning. So we can say from this graph that tornadoes are much more likely to occur in the spring, but they really can occur most any time of day and most any time of the year. Our favorite time to get tornado activity, our favored time, is between about 3 and 7 o'clock in the afternoon. But who would think 6 o'clock in the morning, Christmas Eve? Tennessee tornadoes by county. This also is from the National Weather Service. And you can see a pattern that in East Tennessee, you're relatively your chances of tornadoes go down. I won't say tornado free. And two counties stand out, Davidson and what is that? Shelby County, right? Shelby County is the Memphis area. So were there really more tornadoes actually there or just more tornadoes reported? That's a pretty good question because the population density is really high and even a small area of wind damage is going to be noticed, and then they're going to go back and look at the survey, the aerial survey, and they're going to do damage estimations, and hey, there might have been a little weak tornado there. So there may be some skew, but still note that, what do we got there? Wilson County, Davidson County, and Sumner County all in the 50s. But generally there's a west to east increase or decrease in tornadoes. I thought this was an interesting graphic. This is just a computer swath of all the tornado tracks that have been going on since, that's 56 years when this was made. And here again you can see some real gaps east of the Appalachian Mountains all the way up into New England, not much. And of course the western United States, relatively low risk of tornadoes there. So that kind of defines what is the broad tornado zone in the country. Tornado Alley and Dixie Alley, you'll notice Kansas has 11 annual tornadoes per 10,000 square miles during this time period. Oklahoma's high, Iowa, Illinois, that's pretty much the classic upper or Midwest and Great Plains tornado alley. But Mississippi and Alabama, an average of 10 tornadoes per 10,000 square miles. So there definitely is a Dixie Alley, as they call it now, a southern maximum to tornado frequency. Our problem in this part of the country too is probably at least threefold anyway. One is that our tornadoes have a tendency to be rain wrapped. And we'll talk about that more in a minute, but it's hard to get that classic tornado out in the middle of a field that you can see clearly like you can in Kansas. Our other factor then is terrain. We have hilly terrain, which makes them more difficult to spot. And the third thing is they tend to occur more often at night in our part of the country than they do in the Great Plains in the Midwest. So this has caused us to have kind of a maximum of killer tornado events right over our area. So if you think, well, Tennessee's not really in the thick of the tornado threat zone, that's really not true, especially when we're talking about deadly tornadoes. What kind of conditions do we need to have for tornadoes? Well, we need to have moisture. Moisture source for us is primarily the Gulf of Mexico flow. And a good example is Wednesday. We had a door open at work for a while on Wednesday, and it was steamy out there. You know, the humidity was really, really high. We've got to have a lot of moisture. The other thing we need to have, which may not be so sensible to us as creatures on the ground, is we need to have unstable air. And this really amounts to a sharp decrease in temperature with altitude, sometimes as much as 30 degrees Fahrenheit over 10,000 feet. So we really have to have a big drop in temperature upstairs. We also need a lot of moisture and then dry air above it. That will accentuate this idea of instability. Simply means the tendency for the air to rise. If an area of air, we call it a partial of air, begins to move up, it continues up like a helium-filled balloon almost explosively. So we need instability. There is a measure for that. It's CAPE, which is convective available potential energy. There are all kinds of variation on that. So we look for high CAPE, and we look for some mechanism for lift. I think we all know that cold fronts coming in will kind of undercut that warm, moist air and cause upward movement. There are other things that can do that. Thunderstorm outflow can cause like a miniature cold front to set off other thunderstorms. We also need, and this is a little more subtle, but we need diverging upper winds, because if the wind flow, if the streamlines are going out like this, it's creating more or less a tunnel effect, or a chimney effect would be a better way to say it. We're moving air out, spreading it out, so that compensating flow then causes even more lift. So these are some of the general conditions for thunderstorms. For tornadic thunderstorms, we need another ingredient, and that is wind shear. There are two kinds here. There's speed shear, where the wind increases with height. The other kind, which almost always occurs coincidentally with speed shear, is directional shear. When you look out on a day when we're supposed to have storms and you see the low-level clouds zipping out of the south, maybe at 50 or 60 miles an hour, and then when you catch the mid-level clouds or even the upper-level clouds moving out of the southwest at a big angle with the low-level clouds, and they're moving fast also, well, that's a definite problem. So this wind shear, this change in direction with altitude, is something that we need to quantify. There's the upper shear, and then there's the lower ground level shear, which is really important to the formation of tornadoes. So we look for a day when there's a big weather system coming in. These are big waves in the jet stream. You know, the jet stream just doesn't blow straight west to east. It has all kinds of undulations and waves on it. And when one of these big waves is coming in from the west, it's going to create a lot of wind shear, and that's another thing we look for. Thunderstorm basics. Well, in any thunderstorm, it's kind of like putting a pot of water on the burner, and you turn the burner up, and you're going to get little bubbles of steam forming in the bottom of the bubble, or the bottom of the pan. Those bubbles are going to go up. Kind of like the cumulus clouds on a summer day. They begin to build and build and build, and finally they build to the stage where you get rain produced. The rain dragging down the air creates a downdraft. When you're standing outside and there's a big thunderstorm coming, you feel that rush of cool air. That's the downdraft. The rain, descending rain, dragging air down with it and cooling it in the process. So that's the downdraft. The input to the thunderstorm is an updraft. That's an area that is drawing in warm and moist air, and everything is moving up. The difference in those air streams causes a lot of friction, and just like dragging your feet across the carpet on a winter day produces a spark, those opposing streams of air rub off a lot of electrons, and that's the electrification of the thunderstorm. That's the genesis of it. The strength of the updraft in particular is going to determine how much lightning you get out of this big Van de Graaff generator. So one of the things we look at in terms of trying to estimate how strong a storm is simply the lightning count. Almost always when they superimpose the lightning strikes on television, you'll notice the storm that they are the most concerned with is the one that has all the lightning in it. Not always, but most of the time. Eventually, with our garden variety thunderstorm here, the downdraft will get big and spread out, and it will undercut the updraft, and that effectively ends the storm. In other words, there's no more energy flowing in, it's all just cool air coming out. So an average thunderstorm might last 5 minutes, 10 minutes, 15, 20. These are the pop-up kind of summertime storms. Rapid life cycle. Not severe, although when they collapse, they can produce some damaging winds just from that cold air rushing out, but not usually a severe weather maker. This would be more the single cell end of the spectrum. Another signature we get a lot on radar are lines, long lines of thunderstorms that can produce damaging winds and even weak tornadoes. But the primary focus in tornado forecasting is where are we going to see supercells? Those are those long-lasting, steady-state thunderstorms that go on for a long time. Eventually they rotate, and those are the ones that produce the majority of intense tornadoes. In fact, virtually all intense tornadoes. So a supercell, the basic thing that goes on there in simple terms is the supercell becomes tilted. A lot of that is because of the wind shear environment. But if the supercell tilts, then the downdraft no longer interferes with the updraft. They can remain separate. And that causes them to have a long life cycle. All right, so they continue to draw in environmental air from a wide area. Generally speaking, it is a more dangerous signature on radar to have 2 or 3 supercells than it is to have a great big cluster. Because in the cluster case, they're competing for energy. When they stand out by themselves, they're able to draw in lots of juicy air from many miles around. This is a picture of a supercell, some of the elements of it. There are areas where there is a rain-free base. There's a flanking line, kind of like a miniature cold front from this thing that produces other building clouds. They are a mammoth cloud that are very easy to see from, what would you say, Paul, 75 miles away. You can see the tops, maybe 90, maybe 100, depending on the sun angle. If you've got a flat terrain, that cauliflower head top, and eventually it forms an anvil top as the high cloud part of this actually reaches the stratosphere and is flattened off by the stratospheric inversion up there. But big time clouds. This is a schematic. The inflow area is usually an area which is rain-free, and the downdraft produces like a miniature cold front that comes out. And when that hits you, you'll know it, because again, that'll be marked on radar by usually a gust front boundary. You can see it on radar, and a lot of interesting weather there. Paul's going to talk about some of the clouds that are visible there. Tornado formation, we've learned a lot more about that over the last 20 years, and it requires a strong updraft. There's no question about that. But also something else that's interesting in tornado formation is some of that downdraft air, usually from the rear flank downdraft. It's cold and it comes down, and there's a lot of turbulence and rolling of the atmosphere at that point. So there is horizontal rotation as that downdraft intersects the warm environmental air. And it appears that what's going on here is that horizontal rotation, as it is being sucked into the updraft, is converted to vertical rotation. And just like an ice skater, when you draw your arms in, conservation of angular momentum dictates that you're going to spin faster. Well, that same kind of momentum transfer is going on in the tornado. and that's the spin-up mechanism. Not all supercells produce tornadoes. One of the things that has to happen is the suction of this updraft has to be very strong. If the suction is too weak, or the downdraft air is just a little too cold, then you really won't see a tornado produced down near the ground. One of the things in our practical experience in forecasting the weather is we found that you're almost always more likely to have a tornado when you've had morning rain, when there has been a storm earlier or at least rain to really saturate that boundary layer. Down near the ground, the boundary layer has to really be saturated for you to have a good chance at an intense tornado. So the moisture down near the ground is really important. We look at what's called the lifting condensation level. That's the area where cumulus clouds begin to form, and that's going to usually be 3,000 feet or lower on a tornado day. If the air is drier and clouds are forming much higher, you're going to have to juice up the atmosphere to see intense tornadoes. But this is the current theory on tornado formation. Radar presentation, kind of interesting. The hook echo is part of that inflow pattern. That inflow is not producing precipitation, and so you get a hook. This is a picture of the Joplin tornado, which occurred in 2011, and this was kind of a rogue tornado. There weren't many tornadoes on that particular night. But it was a killer tornado in Joplin, Missouri. The pattern on the left is the depiction there is reflectivity. Rain scatters energy back into the radar, and that's a measure of how reflective the environment is. So that's just intensity of signal. The dark little area near Joplin there is because the signal is so strong because automobiles and pieces of buildings are very reflective radar targets. That's the debris ball. And on the right is storm relative velocity. The radar has been refined to look at weather, and this is a S-band radar, 2.7 to 3 gigahertz band. And not only it's a coherent system radar-wise, so they can measure not only the strength of the signal, but also the phase changes in the signal. And it's those phase changes that determine velocity to and from the radar, away from or toward the radar. And you know about the Doppler effect, right? So if you enlarge this, some of those pixels that are very close together are defining a wind shear of 208 miles an hour indicated by radar. That storm probably had at the ground more like 260 mile an hour winds. One of the things that happens when you're looking at radar, one of the limitations is because of the curvature of the Earth, if you get very many miles from the radar, you're actually looking thousands of feet into the cloud. So most of the time when they show you a circulation on radar, on television, for example, you're actually looking at a slice that's probably anywhere between 3,000 and 10,000 feet above the ground. Just because there's rotation there doesn't mean there is on the ground. Those pixels are pretty wide. They're going to represent something on the order of a half a mile at least at that range. So seeing an actual tornado velocity couplet, the to and from, away from and toward the radar, to see them, an actual tornado would have to be pretty close to the radar. Usually the rotation we're seeing is a mesocyclone. It's that big updraft area that is rotating. So this is some imagery I took off my phone. There's an excellent app called Radar Scope that you might want to get if you don't have it. And so I was sitting there at home watching the tornado just to the south of me down in the Spring Hill area. And to the upper left is a storm relative velocity pattern. There you see the hook echo forming with the dry inflow, the dry slot there. And that was just to the northeast of Columbia. And most remarkably, the upper right one is a new product that we've had over about the last 10 years called correlation coefficient. And I'll give you a quick explanation of that. The radar now, since it's been retrofitted in the all the weather service radars about 2010, they changed the antenna, they changed the electronics and the signal processing and everything. So now they send out a vertical pulse, and then they send out a horizontal pulse. And then you compare the signals that you get back. Most of the time, those signals, the correlation coefficient ought to be very close to 1. That's the red and the orangish areas there, because most of the atmospheric targets are going to be nearly spherical. So the horizontal and vertical components are going to be about the same. In that case, with the bluish colors there, the correlation coefficient is down to about 0.4 or 0.5, which means, hey, these targets are no longer spherical. They're very irregularly shaped. And most pieces of buildings that are flying through the air are. So this is a great way to actually spot debris aloft. So that indication there, just to the east of I-65, that long little road right there, can you see this road right here? That's I-65. So just east of I-65, there was debris in the atmosphere about 5,000 feet in the air. So you know you had a tornado there. And there's a picture of the CC, the correlation coefficient out of Nashville. So yeah, interesting stuff. Let's talk about intensity of tornadoes. The Fujita scale, Ted Fujita was a scientist at the University of Chicago, and he came up with this scale back about 71. So in the 73 tornado, he did a lot of refining. Earlier, he had like an EF6 or EF7 and on up there. He did the research on building damage, going backwards, looking at buildings and trying to figure out how strong the winds must have been. And his initial research was actually done in Nagasaki and Hiroshima to try and estimate how strong the winds were from that bomb explosion, because it was largely wind energy that blew most of the buildings down. So this has been changed now to an enhanced Fujita scale, and there we go. The EF0, the most common type in Tennessee. We have 31 tornadoes on average in Tennessee each year, and the majority of them are EF0s and EF1s, short-lived, last 10 or 15 minutes, and have kind of minimal winds. And then you go on up to the incredible EF4 and EF5, and that's a rarity. About 3% of all of our tornadoes in Tennessee are EF4 or 5. There's only been one EF5. A few EF4s, but they account for about 75% of all the deaths. So that's where the real problem is in terms of public safety. So what does the damage from tornadoes look like? An EF0 up there, well, you're going to have some shingles off, maybe some guttering moved, and you know, that kind of superficial damage. An EF1, you begin to remove roof decking, you have a lot of tree damage. EF2, the roof is usually gone. EF3, you begin to see major problems with outside walls. EF4, most everything is swept away, substantial tree damage. And in EF5, everything is swept clean. And particularly in EF5s, you get these stories about incredible movement of automobiles and vehicles. 60-ton railroad trains, engines moved off the tracks, and you know, just incredible stuff like that. But in general, what we do is there's no way on radar to say, look, that's an EF4 tornado. Can't be done. But what we do, what the Weather Service does, is they go back, take their trained folks, and they look at the damage. And they say, okay, where was the path on this thing? Where did it start? Where did it end? How strong were the winds based on what kind of wind damage? So we always just go backwards on that. Nobody knows looking at the radar. I mean, you can get an idea that it's a big tornado. Even visual observation, it's tough to tell. But visual observation is still very, very important. When I was doing the weather, we always had the National Weather Service communication up. That was primarily where reports from the amateur radio community were funneled into, and that was a major thing that we relied on. They still do today. Social media reports like that. The remote sensing technologies are fine, but actual observation is still very important. Which brings us to the second part of our presentation. Paul is going to talk about what do we look for when we're spotting for tornadoes.
Yeah, I'll need to swipe your book.
All right. Take that one.
Need the other one too. Okay, as Ron was saying, you can see the visibility and what all transpires, in damage, but observing is very important. And I'm not encouraging anybody to go out and hunt for tornadoes. That's very highly discouraged here in Middle Tennessee, and Ron touched on it. Part of it is rain wrapping. The other part is the obscurity of our hills. You can't see things. Where I was raised and grew up was on the flatlands. So in the Ham community, we were sent out to look for tornadoes. But down here, it's not recommended. What are things you need to know? Well, as Ron was mentioning, it's all about time of day and location, location, location. It's like real estate. If you're not in the right spot, you won't see it. Viewing position, very critical, and we'll go into that in some depth here. Time of day, as Ron mentioned, most of our tornadoes are at night. You're not going to see it. Only thing you'll see are transformers blowing up or lightning maybe highlighting it, but other than that, and that means you also have to be in that clear slot. Radar, hugely important. As Ron mentioned, back in February when I did a presentation, I gave a lot of you directions on where to find radar scope, GR level 3, all that kind of stuff from Gibson Ridge. There's a lot of tools out there. I recommend you take advantage of that because at least you'll know what's happening in your immediate area. But at nighttime, you've got rain and low clouds that are just obscuring the tornadoes. So you have a hard chance of even seeing it. And then once again, watch for the power lines and transformers blowing, and you'll see video like that. And on Ron's little clip from back in 1998, you could see that, and that was daytime. So it's really important to realize the difference on what is a wall cloud, what is a funnel cloud. And Laura and I we all in violent agreement. You can't reinforce enough the differences in being able to recognize it. So we'll be presenting a couple examples of fake tornadoes. But in the case here on the left, that's an actual, you're on the prairie, here you go, you're out in open land, that's a funnel cloud. On the right is the tornado dropping out, or the wall cloud rather on the left, the funnel cloud's on the right, and you can see it starting to descend. You've got to watch for those components. And sometimes, this is really important, there could be a second one right behind it, out of the same thunderstorm. Ron was talking about the winds rotating and cycling. In this particular example, there's the forward tornado, there's the rear. Same thunderstorm. It can happen. So a lot of folks, misinterpret and say, well, one tornado per thunderstorm. Not necessarily. You could have multiple, what they call vortices inside one thunderstorm, and you can get multiple tornadoes as well. So be aware, there's a lot of differences. It's not just so simple, one thunderstorm, one tornado. Shelf clouds, we talked about this back in February, but I want to reinforce the importance and some differences. When you have a squall line, which is a line of thunderstorms approaching your area, many times you'll have an advanced cloud called a squall line, or a system called squall line, and the shelf cloud comes out of that thunderstorm. It's enhanced by it. But I heard this on the radio back last year. I saw it on MTIRS one time. So I saw a roll cloud. I saw a roll cloud. Wasn't a roll cloud. It was a shelf cloud. We don't get roll clouds very often, if ever, in Middle Tennessee. The reason roll clouds look so unique, they look like a roll of dough, when you're rolling out dough. And it's flowing air that's caused by very saturated air. So it's sort of like what we had the other day. Saturated, you go outside, you feel it. But you have to have a couple of key components. One is the warm air, and then a cool wave of air proceeding forward. And they're most likely seen in Florida and California, because that's where you have those kind of temperature, saturation, and wind events where they will roll in. You have the rolling fog in San Francisco, but when you look at this type of cloud, there's nothing behind it. It's not associated with a thunderstorm. So when you're identifying out in the field, we see wall clouds, shelf clouds here in Middle Tennessee. We don't see roll clouds. Very important distinction. So when you're talking to or calling in a report, you'll see usually the shelf cloud first many times, and I'll show you another photo of how it's integrated into the thunderstorm. But this is usually a big indicator of squall lines or an outflow boundary, as Ron was talking about. So here's an example of other cloud lowerings. You have the wall cloud versus a shelf cloud. Wall clouds on the left, shelf clouds on the right. And you can see you're out in the prairie, it's easy to see them. Where here it's a little tougher. Back in February, I showed a couple of pictures from my home where we had this huge shelf cloud come through, and behind it was thunderstorms. But you don't typically have a tornado right in a shelf cloud most times, but they do happen. And then there's the fake lookalikes. I love it when people call in, oh, I see something. Well, let's talk about what you see. Scud clouds. They hang down, they protrude from the cloud. That looks like a funnel cloud at first glance. But what you need to do is you need to watch it. If you're seeing something like that, you have to look for rotation. Be patient. Give it a minute or two and see if you see that rotation that is typical of a tornado forming. And the wall cloud rotates. As you saw in that video Ron showed, you saw that thing just rotating around and the tornado was in the center of it. Same thing here. If you don't see rotation, it's not a funnel cloud dangling down. It's a scud cloud. It's just the wind and the moisture of a draft going on causing condensation. And then there's rain shafts. This is also a look-alike type device. People get faked out by that. Well, look at that, it's coming out, it's got to be a tornado. No, it's just rain coming out of the cloud. Same on the right. It looks sort of evil, you got the sunlight behind it and everything. It's a dramatic photo, no question, but it's just a rain shaft. There's no rotation going on. It's just watch it move laterally. If there's no motion counterclockwise, it's not happening. So one thing we learned when I was in spotter training a number of years ago is there's a certain location that you need to be in to actually see the tornado. And someone took some video of Wednesday's storm in Spring Hill, and they were showing it. I saw it on Channel 2. I don't know if they had it on the other networks. I just happened to be watching that at the time. But someone had a cell phone shot, and you'll see it where the tornado is running through Spring Hill and going into the high tension lines. Some of you may have seen that, and then it moves across the screen. That person was in the lower right-hand corner in the dry slot area where you have some visibility if it's not rain wrapped, and they actually could see it. But it's not as it's not as beautiful as you can see the sunlight behind like out in Oklahoma. Here you had lots of clouds, but there was enough daylight coming in behind that you could see the tornado. So if you're going to be looking at it, the only chance you have to seeing it, unless you're right next to it, is on the lower right side or on the southeast side of the storm here in the northern hemisphere. So if I go back to December 9th tornado, we had daylight that day until, I think it was about 3 in the afternoon, Laura, when that one started up, that whole series out to the west. And you can see there's multiple thunderstorms. And when I covered this in February, the point was you had literally tornadoes in several of these simultaneously. So where would you need to be to even see it? Well, if you were to the west of Nashville, because it was all tracking to the northeast, you might have had a shot of seeing one of those if you were close enough. But look at all the hills we have here from Leaper's Fork going up, you just don't have the visibility. But if you're lucky, you can get to see it. If you see this kind of formation on a radar, that's a squall line. And don't go spot it. Don't go out of your house. 60, 70 mile an hour winds, 80. They were forecasting the other day, there was 80 mile an hour winds in some places out in Camden County, east of me. You want to put as many walls between you and the outside as possible. Get to that safe place. Be smart. Don't go out and look for it. That's not a safe thunderstorm to be standing in front of. So if you see that long arc, that's a lot of wind action heading toward you. And here's some rain-wrapped tornado examples. You can see it, you can sort of see them. But sometimes, depending on light, backlighting, your position in relation to the storm, you may or may not see it. But a lot of these are shot out in the flatlands of Oklahoma and Kansas, where you can get a better shot at possibly seeing it. But around here in Middle Tennessee, as Ron stressed, we're rain wrapped most of the time. You won't see it. So important to have the radar. Pop quiz. Is this a shelf cloud or a wall cloud? Ooh, no guesses. Ron's already seen it, so he can answer.
I think it's both.
It's both. Yes, you can have a wall cloud with a shelf cloud in a thunderstorm. There's a whole science. We could spend a day just on cloud identification and the varieties within a thunderstorm when you're looking for tornadoes and the different types of clouds, etc. It's not as clean cut as what I just showed you all the time. That's just so you can grasp the idea of what's a wall cloud, what's a shelf cloud, what's a funnel cloud. But in this case, it's both. And it can fool you. So, as I stressed back in February, safety first, safety first, safety first. It's best to heed the warnings, and when they tell you to go to your safe place, go to your safe place. Some of these folks go out, oh no, I don't want to go, I want to go capture this thing, and then they're hit by flying debris. Follow the radar track. Back in 2023, gave you a lot of overviews, or in February of actually this year, I got my dates wrong. I gave you all kinds of alternatives for radar and how to observe. Observe from home. Be safe. Stay at home. Keep an eye on things. See what's coming. Listen to M-Tiers. They give you the play-by-play, and Cliff streams it. So there's all kinds of options to get radar if you don't have it. If you're mobile, try to find a safe place to take a shelter. They talked about people, one of them survived, right, on 65 there, drove right into the tornado, and they couldn't find the guy, and he was eventually ended up at the hospital somehow. They still don't know how, as of last night. You don't want to be driving in this stuff. Get into a safe place, find shelter, move diagonally from it. I mean, part of our training we had was how to drive away from the tornado safely, because they're moving very quickly. They're 40, 50, 60 miles an hour. They will outrace you in your car because you don't know exactly which way it's moving when you're out there driving. So get to a safe place, know your escape routes, and you move away at right angles is the best recommendation. So what are considered safe places? Just a reminder, your interior rooms of a house. That would be, if you don't have a basement, interior bathrooms, someplace without a window, someplace as far away from the outside walls as possible. If you have a storm shelter, you're blessed. I don't have one, but my daughter built one in her new house. So she learned and paid attention to Dad. And where are the safest places in your house? Look around your home, try to find where that is. And if you live in manufactured housing, mobile type homes, there are places you can go when the warnings start to get issued. You should proceed there and not stay in that kind of building. You've got the National Weather Service. Have a weather radio. Have your ham radio. You've got all kinds of alternatives, local media on TV. And be weather alert, weather aware. As I said back in February, you can see this stuff coming 5 days in advance. You know something's going to happen. Pay attention, be weather aware, and our local meteorologists do a great job getting that out in advance. So with that, thank you for your interest today, and Ron and I can field questions.